Vacuum energy is all around us. It makes the universe expand with quantum fluctuations. And before you know, they're talking about energy chakras and quantum healing. Even many physicists and science writers are very confused about what vacuum energy is. But don't despair. At the end of this video, you'll know why it's not what you were told it is. This video came out of my desperation over a letter that was published in the June 2021 issue of Scientific American. It's a follow-up question about an article about the accelerated expansion of the universe, and it reads as follows. Cosmic Conundrum by Clara Moskowitz describes how the most likely cause of the accelerating expansion of the universe is vacuum energy, the effect of virtual particles popping in and out of existence. But it does not explain why vacuum energy would cause the universe to expand. I would think that if space is filled with evanescent virtual particles, they would collectively exert a huge gravitational force that would counteract expansion. Chris Martiniak, Berkeley, California. The editor replies to this. Vacuum energy is positive and has a constant density throughout space. Thus, increasing the volume of space increases the total amount of vacuum energy, which requires work. It's the opposite of a gas whose energy and density decreases as it expands. When that happens, the gas exerts positive pressure. In contrast, because vacuum energy is positive, it exerts negative pressure, so galaxies on the larger scales are pushed apart, not pulled together. I didn't understand this answer, which is a little bit embarrassing because I'm one of the people quoted in the original article. So I want to look at this in a little bit more detail. First of all, the terminology. What's vacuum energy and why is it important? If we leave aside gravity, we can't measure absolute energies. We only ever measure energy differences. You probably remember this from your electronics class. You never measure the electric potential energy. You measure differences in it, which is what makes currents flow. It's like you have a long list of height comparisons. Peter is 2 inches taller than Mary, and Mary is 1 inch taller than Bob, and Bob is 5 inches smaller than Alice, but you don't know anyone's absolute height. Energies are like that. Now, this is generally the case, that you can only measure energy differences as long as you ignore gravity. Because all kinds of energies have a gravitational pull. And for that gravitational pull, it's the absolute energy that matters, not the relative one. So it really only becomes relevant to talk about absolute energies in general relativity, Einstein's theory for gravity. Yes, that guy again. Now, if we want to find out the absolute value of energies, we need to do this only for one case, because we know the energy differences. Think of the height comparisons. If you know all the relative heights, you only need to measure the absolute height of one person, say Paul, to know all the absolute heights. In general relativity, we don't measure Paul, we measure the vacuum. How do we do this? For this, we need to have a look at Einstein's equations for general relativity. Here they are. They are called Einstein's field equations. They contain two constants, which means these constants have the same value at every point in space and at every moment in time. The one constant, the g, is Newton's constant and determines the strength of gravity. The other, the lambda, is called the cosmological constant. The r's here quantify the curvature of spacetime. And this term with the t contains all the other kinds of energies, particles and radiation and so on. This means if we set the t term to 0, we have empty space. One can therefore interpret lambda as the energy density of the vacuum. So not the entire energy, but energy per volume. This vacuum energy density doesn't dilute if the universe expands because it's a property of spacetime. That makes it different from all other kinds of energy densities that we know. The other ones, for example for matter or radiation, all dilute with the expansion of the universe. The vacuum energy doesn't. What does the energy density of vacuum have to do with the acceleration of the universe? If we want to know what the universe does as a whole, we introduce what's called the scale factor A. The scale factor tells you how distances change with time. So A is a function of time, A of t. If the universe expands, A increases. If the universe shrinks, A decreases. You plug this into Einstein's equations. And then one of the equations says that the second time derivative of the scale factor, so that's the acceleration of the expansion, has a contribution that's proportional to the cosmological constant. So that's where it comes from. A positive lambda makes the expansion speed up. What's this all got to do with quantum fluctuations? Nothing. And that's where physicists get very confused. You see, we cannot calculate this measurable vacuum energy density which appears in general relativity. It's a constant that we infer from observations, and that's that. A lot of physicists claim that particle physics predicts the vacuum energy density and it's 120 orders of magnitude too large, and that's the worst prediction ever. I'm sure you've heard that story. But that's just wrong. This value which you get from particle physics is unmeasurable, so it's not a prediction. If you hear someone claim it was a bad prediction, I suggest you ask them what theory was ruled out by the conflict between the prediction and observation. The answer is none. And why is that? It's because it wasn't a prediction. Okay, so we have learned vacuum has an energy density. It's a constant of nature, it's proportional to the acceleration of the expansion of the universe, and it has nothing to do with quantum fluctuations. This hopefully also clarifies how something that's supposedly due to fluctuations can be constant both in space and in time. It's because nothing is fluctuating. So that would have been my response to the question. Let us then look at the editor's response. This response uses an analogy between the vacuum energy density and the simplest type of gas called an ideal gas. An ideal gas is just a bunch of particles moving around, bumping off each other. The ideal gas has a volume, temperature, pressure, and an internal energy. Internal energy is what you need to do work. The key equation is delta U equals minus P delta V. U is the internal energy, P the pressure, and V the volume. Those deltas mean you have small changes of the quantities that come after the delta. The pressure of an ideal gas is always positive. What this equation tells you is that if you increase the volume, so delta V is positive, then delta U is negative, so the internal energy decreases. This means if the gas expands, it does work, and then you have less internal energy left. Makes sense. Now, as we have seen, the energy density of the vacuum, lambda, is just a constant. The total energy is just the density times the volume. This means if the volume increases because the universe expands, but the energy density of the vacuum is constant, then the amount of vacuum energy increases with the volume. If you identify this energy with the internal energy of a gas, this means delta U has to be positive. And if delta V is also positive because space expands, this can only be if the pressure is negative. And this is correct. If you associate a pressure with the vacuum, then that pressure is negative. However, the problem with this explanation is that the vacuum energy is not an internal energy, it's a total energy. And the vacuum energy is not a gas in any meaningful way because it's not made of anything. And how you get from the ideal gas analogy to the expansion of the universe, I don't know. So I don't want to call this answer wrong, but I think it's misleading. It strongly suggests a physical interpretation, namely that the cosmological constant is some kind of weird gas, but it doesn't spell out that this is really just an analogy. I'm picking on this because simplified analogies like this that make no sense if you think about them are the reason so many people either think physics is incomprehensible or physicists have totally lost it, or maybe both. If you look at the math, The best way to think about the vacuum energy density is that it's just a constant of nature. This video was sponsored by NordVPN. Do you also sometimes think you should be more careful with the data you submit on the internet? The best way to do this is to use an encryption protocol, and NordVPN makes this super easy. It's an app that you install on your phone or laptop, use it to connect to one of their servers, and then you browse the web from there. This keeps your data safe, even on a public wireless. NordVPN has more than 5,000 servers all over the world and allows you to choose your location from any one of them. Besides keeping you safe, this also means if you encounter a video or website that is blocked where you are, you can just connect to a server in a different country and access the website from there. Viewers of this channel can now benefit from a special offer with a huge discount if you use the link nordvpn.com/Sabine and the coupon code Sabine. NordVPN is super easy to use and works on pretty much all operating systems. Once again, that's nordvpn.com/Sabine and the coupon code Sabine. Thanks for watching. See you next week.